Hi, my name is JHarmon. I'm taking all 3 classes, and I'll be talking about the radio receiver system for KI5. The radio receiver starts with an antenna and ends with an analog to digital conversion. This antenna converts a radio wave signal to an electrical signal that can be processed by the radio system. Typically, the signals are transmitted in terms of ones and zeros, where a voltage threshold determines if a 1 or a 0 is registered. The downside to this sort of transmission is that a high frequency is required in order to deliver data at a fast enough speed. This high frequency of the radio wave means that the signals attenuate much faster compared to their lower frequency counterparts, and as such, reception in buildings, for example, degrades very rapidly. As wireless communication continues to move towards higher frequencies, the density of radio towers must also increase to combat the increased attenuation, transforming the wireless communication network to an array of cell tower nodes. As seen on the screen, the antenna comprises the majority of the receiver system. Printed in layers, the antenna forms a 3-dimensional structure to maximize the length of the antenna for the same volume. Since the antenna is embedded in the PCB, the speed of the radio wave, and therefore the wavelength, is reduced compared to air. With this in mind, the size of the antenna is such that the wavelength of the expected frequency in the material is roughly equal to the length of the antenna. Note the transmission line that runs along the middle of the PCB. Given that it forms a microstrip line with the conducting plane on the bottom of the PCB, its impedance can be calculated. Neglecting the fringe effects, the impedance of the line is roughly 90 ohms. However, this approximation is poor due to the relative size of the transmission line. Factoring in the fringe effects, the impedance is roughly 50 ohms. Intuitively, the fringing effectively includes the lower dielectric material in the calculation, which accounts for the lower impedance. The next stage in the radio system is the bandpass filter. An example of a bandpass filter is shown on the screen. This filter selects a band of signals attenuating frequencies outside this range. So even though the antenna receives the sum of the electromagnetic waves in the air, in frequency the signals are well separated and can be isolated from each other by the bandpass filter. The frequency of the received signal depends on the carrier frequency of the radio station. Around this carrier frequency, there exists a bandwidth which would contain a modulated voice signal, for example. In practice, the bandpass filter extends just beyond this bandwidth of the desired signal around the carrier frequency. An example is shown on the slide of a transistor circuit that performs this bandpass function. At either end of the frequency spectrum, towards 0 or infinity, the output is attenuated heavily, ideally having a gain of 0. Within the cutoff frequencies of the circuit, determined by the poles of the system, the gain reaches a maximum, achieving the desired effect of selecting a band of signals. There are 4 main types of specific filters to implement this bandpass requirement: Bessel, Butterworth, Chebyshev, and elliptic. In exchange for more selective filtering for the same order of the filter, the Chebyshev and elliptic filters produce ripples in the passband. A figure depicting these types is shown on the screen. One simple way to produce a bandpass filter is to place a low-pass and a high-pass filter in series. Another way is currently shown on the screen. By making the transformation as shown, a low-pass transfer function can be turned into a bandpass transfer function. The next stage is a low noise amplifier. This processes the filtered signal for the mixing stage while preventing significant distortion. If the amplitude of the input at the mixer is too low, it won't function properly, so the low noise amplifier makes sure it's at the proper level. In the mixer, 1 copy of the signal is sent to the baseband and 1 is sent to higher frequency. For example, with a signal around 10 kHz carrier frequency, 1 copy would be demodulated to the baseband while another would be sent to 20 kHz. Since the frequency response is symmetric, technically 2 copies are sent to the baseband, while 1 is sent to negative 20 kHz and another to positive 20 kHz, explaining the amplitude difference between the baseband and the 20 kHz signals. One of the most important frequencies in mixing is that the phase of the carrier frequency are identical between the phone and the radio tower. In order to accomplish this, cell phones periodically sync with the radio tower. These amplifiers and filters are implemented like the op-amp shown on the screen. Assuming the amplifier is ideal, the open loop gain is infinite, and the closed loop gain is simply the ratio of the two impedances as shown. However, assuming the op-amp is not ideal, the open loop gain and the pole of the amplifier on its own has to be factored in. This results in the transfer function as shown. As long as A is a large value, the output of the amplifier is largely unaffected, since even though the pole of the op-amp on its own is very low, the feedback of the op-amp that has been added sends this pole to a very high frequency, again as long as A is a very large value. Note that the impedance are complex and can be represented by capacitors and inductors in addition to resistors. In implementation of the bandpass filter, for example, a very narrow band typically requires 5 to 10 op-amps, which adds significant cost to the system. As this band becomes narrower as well, manufacturing tolerances have a much more significant impact on the filter, potentially ruining the desired function of the bandpass filter. Certain other methods in design, like increasing VSAT, help reduce noise by placing the transistors deeper into saturation. Of course, this has the negative effect of reducing the swing, but in many cases this trade-off is necessary. In summary, a radio receiver system requires many components working in tandem and an understanding of microelectronics, electromagnetics, and signal processing. Thanks.